So 7.2 parametrics again, this time accumulating instead of changing, differentiating. We'll be integrating. All right, so just another clarification. We did this when we started the last video, displacement versus distance traveled. They're only the same when you have linear motion and you're traveling in the positive direction. But for parametrics, they're actually very different because one of these is going to be a single number and the other one's going to be a pair of numbers. So when you're finding displacement for parametrics or vectors, you're going to be finding the component displacements. You're going to be figuring out the horizontal displacement and the vertical displacement as two separate calculations. Right? There is no like equivalent displacement along a curved path. But there is a distance traveled along the curved path. And as we mentioned in the previous section, it's going to be the integral of the speed, which is, of course, the integral of the norm, which is the Pythagorean theorem, hypotenuse, right? And that's also the arc length. So we're going to be doing exactly what we did in particle motion back when we did linear motion. We're just going to be doing it twice for displacement, and then we're going to be finding the arc length for distance traveled. So here's an example. Calculator permitted. An object instead of a particle. That's a radical difference, isn't it? Not really. An object moving along a curve in the xy plane has its position given by that. So kind of a vector format, no chevrons, but still as an ordered pair. At time t with dx dt is that, and dy dt is that. At t equals 2, the object is at the position 1, 4. So there's an initial condition. So here's what we know. At t equals 2, the x-coordinate is 1, and at t equals 2, the y-coordinate is 4. Sweet. First of all, find the acceleration vector at t equals 2. So I'm going to go ahead and treat this as if it were an actual calculator question where you could use your calculator exclusively. Let's go ahead and put it in parametric mode. And you can stay in parametric mode. And now I'm going to go ahead and type in y1, I'm going to type in my derivative equation. So I'm graphing the velocities here. So that'll be t sine of t. And then in y sub 1, I'm going to be sketching my vertical velocity, cosine of t squared. And we'll get rid of all the other stuff. Oh. I'll just type it all in again. And of course, what mode should we be in? Degree or radian? Radian. All right. So I have them in there. I double checked, triple checked. It looks good. Find the acceleration vector at t equals 2. So with those in your calculator, all you have to do is show your notation. So I'm going to go ahead and say that my velocity vector prime is going to be my acceleration vector. So by doing that, again, we're defining what A is in terms of the velocity, what's given. And because I'm given dx dt and dy dt, I'm going to define that, first of all, by x double prime of t and y double prime of t. So what I just did there is I switched from Leibniz notation to function notation, which is okay. All right? You can certainly do that. Bless you. So essentially, I've defined my acceleration in terms of the two equations that are given. Now that I've done that, I can actually plug in a 2. So I can either rewrite it or, believe it or not, I can do this. I can just change all those t's to 2's. Because I'm doing this on the calculator, I'm not actually going to be finding the derivative equation and then plugging in. So it saves a little bit of writing. But you could write it in terms of t and then underneath it put it in terms of 2. All right, so now I have two calculations to do. I need to figure out what the second derivative is at 2. Well, my first derivative of x is in x sub 1. So from the home screen, if I hit alpha trace, look what shows up now. Not y sub 1, y sub 2, y sub 3, but I have all my parametric guys right there. So x sub 1 is 1 and y sub 1 is 2. So in x sub 1, remember, I have the derivative. So I'm going to take the derivative of it from the home screen. So the math 8, it would be actually my first keystroke. I'm going to take the derivative with respect to t of my function that's in x sub 1, and I'm going to evaluate it at 2. So it's kind of the same keystrokes, but your calculator in parametric mode will use t, and it has your x sub 1 and y sub 1s instead of just your y's. And you hit enter. Boom. And then you write it down to 3 decimals, 0.077. And then you do the same thing for the second derivative. So mass 8, and with respect to t, alpha trace, this time we want to take the derivative of the y, so that's number 2, and also evaluate it at 2. And you get 3.027. So again, if this were exclusively a calculator question, that would get full credit. You have the notation shown up above, and then you actually have your answer. So you have your setup, and then the calculator does all the heavy lifting for us. We just need to make sure we report 3 decimals. Even if the third decimal is a 0, right? Yeah, okay. Questions on A. Part B, write an equation for the tangent line to the curve at t equals 2. And when we talk about an equation of a tangent line, we're back to the same old thing. We want y sub 1 plus the slope times x minus x sub 1. So there will be no t's involved in our equation. So what do we need for the equation of a tangent line? All year long we've needed 2 things, a slope and a point. So the first thing we need is the point at t equals 2. So if you want to write that as a vector, how am I going to figure out what the point at t equals 2 is? It gives it to you. Very good. Oh, man. That was a helpful thing. At t equals 2, the position is 1, 4. So we have the point 1, 4. And now we just need the slope at that point. How are we going to find the slope at that point? We almost have it, right? We have dx dt and dy dt. So let's just go ahead and write dy dx at the point 1, 4. You could do it like that. Or you could say dy dx evaluated at t equals 2. Either one of them kind of implies the same moment in time. But it's really the second one that's going to be more useful. Because now all I have to show is y prime of 2 over x prime of 2. dy dt and y prime are interchangeable, y prime and t. Okay, so now I can just go straight to my calculator. I've shown my setup, and now I go back to my home screen. And this time, since I have the derivatives in y1, I'm not going to be taking the derivatives. I'm just going to go alpha y equals to get my horizontal division bar, and I'm going to evaluate the function I have in y1, which is number 2. I'm going to evaluate it at 2, and then I'm going to click down, and I'm going to evaluate the function that's in 1, also at 2. So again, it's a little weird because I'm calling it y1, but I know it's really the derivative of y, and I'm calling it x1, but I know it's the derivative of x. Okay, so there you go. Click enter, and you'll have the value. It's negative 0.359. So same keystrokes, just different symbols. Use the calculator to do the heavy lifting. You're going to get a check for your setup, and you'll get a check for the answer. Now, these equations, you could actually plug in by hand. You don't have to use the calculator here. At t equals 2, dx dt is 2 sine of 2. So you could actually leave it as an exact answer, right? And dy dt is going to be cosine of 2 squared, which is 4. So you could have also had, over here, you could have had cosine of 4 over 2 sine of 2. That would also get full credit. You don't have to have decimals on a calculator portion. But for the derivative of those, I wouldn't spend time doing the product rule here just to plug in a 2, and I wouldn't spend time doing the chain rule here just to plug in the 2. I would let the calculator do it for me. All right, finally, find the speed of the object at t equals 2. Speed at 2. How do we find speed at 2? It's the norm. Good. So I'm going to say the velocity at 2, and then I'm feeling kind of like a double bar there instead of a single bar. Kind of don't get the opportunity to do that very often. And remember, it's going to be the square root of x prime of 2 squared plus y prime of 2 squared. So we have the component velocities, which are x prime and y prime, squared because it's the Pythagorean theorem. And that's all you would need to show for your setup. And then it's time to go to the calculator and I'll take the square root of. Now here I'm going to use extra parentheses. So alpha trace number 1 is my x. And remember, if you open parentheses, 2, close parentheses, that evaluate at 2. And then I close it again and square it. That assures that it squares the entire quantity. And then do the same thing, plus, open parentheses, alpha trace number 2 of 2, close, close, squared. And if you compare that to what you have written on your paper, it should be very, very similar. It's really, really nice with this new math print. Hit enter, and you get 1.932. So your velocities are still 2 numbers. Your speed is always a single number. Okay. Part D. We haven't really done any integrals yet. That's where D comes in. Find the displacement of the object from 2 to 7. Find the displacement from 2 to 7. So for parametrics, is displacement going to be 1 number or 2 numbers? 2, right. We have to find the individual displacements. Distance traveled is still 1. Okay, so displacement is going to be component. It's going to be the integral from 2 to 7 of x prime of t dt. That would give you your horizontal displacement. And then the integral from 2 to 7 of y prime of t dt. That gives you your vertical displacement. And that right there is your integral setup. That would get credit. Now you just go to your calculator and you type in what you have. Okay, so math number what? 9, 2 to 7. And my derivative for x is in number 1. And with respect to t, and we write it down. And I'll put mine in chevrons. I kind of like writing in chevrons. 3, 6, 1, or 3, 6, 2. And then we just repeat the process. I'll just go, whoa, sorry. I'll just go back and scroll and then change it. Alpha trace number 2. That one worked a little harder. So in the 5 seconds, I guess we could say, if you want to make sense of it, in the 5 seconds from 2 to 7, this particle moved a little more than 6 units to the left, while it moved very, very small distance up. Now, it doesn't mean it was moving left the whole time. Doesn't mean it was moving up the whole time. Remember, that's just the net change. It could have moved left and right, but it was just displaced to the left and up from where it started. What's that? Why is it the integral of the derivative? It is the integral of the derivative, right? If you look at what I wrote down on my paper, it's the integral of x prime, right? We're integrating the horizontal velocity. But why did I use x on my calculator? Right. I typed into x1 my derivative function. So that's the thing that's really kind of important to keep track of here. My x of 1 is really x prime of 1. I typed it in. You can't use prime note. There's no symbolic prime notation as placeholders. So you just have to kind of keep telling yourself, my first derivative is in x of 1, my first derivative is in y of 1. And now you're just using a convenient way to recall them. Okay? All right, the next part. Find the distance traveled from 2 to 7. Is that a single number or 2 numbers? That's a single number. And we also call that the what? Well, the net would be displacement. It would be the total gross distance. But we have another name for it. Arc length, right? Arc length. Okay, but I'm going to call it distance here instead of arc length, but it's the same thing. If you travel along the XY plane, the length of that curve is also the distance it travels. So let's go ahead and call it distance this time, but it's going to be the integral from 2 to 7 of your speed function, which of course is x prime of t squared plus y prime of t squared dt. It's just the Pythagorean theorem, but we integrate the function. All right, so now that we have the setup, we just go to the calculator, Math number 9 from 2 to 7. And now we do the square root of my x prime function, which is still found in number 1. Now, because I'm not evaluating it, I can just square it like that without parentheses. And then plus the other one, which is found in alpha trace number 2, squared. And then with respect to t. Does that look good? I like it. Hit enter. And you get the distance traveled, or the arc length is, work it, baby. Come on. You can do it. Oh, man. I'm glad I'm not doing this with my hands. The calculator's struggling with it. I guess you read the next question while you're waiting for your calculator. Find the position. Oh, wait. And then as soon as we get mid-sentence, we have to come back. 13.229. And there are no units here, but that would be units of length, like feet, miles, inches, furlongs, whatever. Furlongs, yeah, you don't want to see that. All right, find the position. So everything leads up to this. Find the position at t equals 1. So where something is at any given moment is a function of where it started plus its displacement, right? We already found the displacement of the horizontal and vertical up here. All we need to do to get part F is to add to each of those displacements the what? The starting position, right? Which x started at 1 and y started at 4. Because those do integrate from 2 to 7. So let's go ahead and set it up. The position at 1, I'm going to call that x of 1, comma, y of 1. And you could do it as an ordered pair or put it in chevrons. It's going to be the starting x value, which, again, I forgot. It was 1. Oh, wait. Let me back up. We're not finding the position at 7. I'm sorry. I didn't even read the instructions. We want to figure out the position at 1, not at 7. So that's a little bit different. So where it is at 1 is a function of where it started, and the x again started at x equals 1, plus the net accumulation from when it was at 1, which was up here at t equals what? 2, right? So this always has to match. Those have to be at the same time. And now we're going to 1. So we're actually going back in time, which is fine. The integral will take care of it. All right, so the starting x value of 1 plus the net accumulation from t equals 2 when it was at 1 to t equals 1 where we're going of x prime. And then very similar for the y-coordinate started at 4, right? Plus the integral from when it was at 4, which is still at t equals 2, to where we're trying to get to t equals 1 of y prime of t. So there's just a lot to keep track of, right? Because we have this third variable now. But we're just doing everything that we did previously. We're just doing it twice. So there would be the integral setup. And now we just have to type it in twice. So here we go. The first one, the starting position for x is 1 plus math 9, the displacement from 2 to 1. And there's no reason to flip the intervals of integration and change the sign out front. Your calculator can handle it from 2 to 1. So don't kind of overcomplicate it. Oops, I just messed that up, speaking of complicating things. All right, alpha trace number 1 with respect to t. And we get this number here, negative 0.44. Do we need that 0? Yes, we do. And then the second verse to the same song, but now we have 4 plus math 9 from 2 to 1 of y prime, which is in alpha trace number 2 with respect to t. Pure point, pure 3. And then you write it down, and you're done. Parametrics, twice as fun, a pair of funs. Do it once for x, do it once for y. That right there could have been a free response question, as you could imagine, right? A, B, C, D, E, F. You probably wouldn't be asked all of those. That's probably worth more than 9 points. But any one of those things could be asked. So if you understand example number 1, and you know how to use your calculator and what to show to get credit, you're well on your way to mastering parametrics. Okay? Any questions on that one? There are two numbers in parametrics or vectors that are single-digit representatives. Everything else is a vector representative. What are the two quantities that are single-number representatives? The speed and the distance traveled. Yeah, that's it. The speed is a single number, and the distance traveled is a single number. Everything else you list as components. All right? Distance traveled and speed. All right, number 2. An object moving along the curve in the xy plane has positions of this. So not derivatives, positions. Not in chevrons, no big deal. For time greater than or equal to 0, with, they're giving us dx dt, or x prime of t. It's 2 sine of t squared. The derivative dy dt is not explicitly given. Dx dt is. At time t equals 2, the object is sitting at the point 3,5. So we have our initial condition again. Part A, find the x-coordinate of the position at t equals 4. This is another sample for your response. Find the x-coordinate of the position at t equals 4. So this is pretty much exactly what we did up here on part F, but we're only doing it for the x-coordinate. Is the calculator permitted here? I'm thinking it has to be. I didn't write it in there. So let's go ahead and change this around now. I'm going to go to y equals. I should have put calculator permitted. So I'm going to type in, once again, into x, I'm going to type x prime, 2 sine of t squared. And y prime was not explicitly given, so that might cause you to say an expletive because you don't have it. But, oh well. Maybe we don't need it. Or maybe they'll have us find it. That'll be good. All right, so let's show our setup here. The x-coordinate 4, so you could call that x of 4. I better switch screens. X of 4 equals what? Someone help me out now. The initial, which is what? 3. My initial x value is 3. Good, so 3 plus the integral from 2 to 4. Good. Of x prime of t dt. And now I can just type it in. So here we go. 3 plus, math 9, 2 to 4. And my x prime is in alpha trace number 1 with respect to t. So we get 2.884. And you write it down. And notice I just brought the equal straight down from where it was above. So that's all you need. Are there any units here that we need to tag on? No. Okay. Part B. At t equals 2, the value of dy dt is negative 6. Oh, okay. Write an equation for the tangent line to the curve at that point. X sub 2, y sub 2. All right, so I need two things for the equation of a tangent line. I need the slope and a point. The point is x sub 2, y sub 2. Do we know what that is? Yeah, that's the point 3,5, right? They gave it to us above at t equals 2. So there's the point 3, 5. And now I need the slope. That's dy dx. Okay, and I need that at t equals 2. Well, that's going to be y prime of 2 over x prime of 2, yes? Do I know what y prime of 2 is? What? Negative 6. They just gave it to me. Wow, that's cool. I needed it, and they gave it to me. X prime of 2, I'm just going to go ahead for now, and since there's x prime, I'm just going to plug it in. It'll be 2 sine of 2 squared, which is 4. So 2 sine of 4. And again, even on a calculator question, that's an exact answer. You can leave it like that. So the equation now, in Taylor form, is y equals the y value of 5 plus the slope. I guess we could simplify that. Let's call that negative 3 over sine of 4. Or how about negative 3 cosecant of 4? Just to have a little more fun with it. So 5 minus 3 cosecant of 4 times x minus the x value. You could have also typed it in if you wanted that as a decimal. You could have recalled your function, alpha trace, nope, not graph. Alpha trace, recall number 1, and plugged in the 2, and that would give you the decimal, okay? So you could also have minus 1.513. But of course, if you're going to use the equation of the tangent line, the exact answer is probably preferred so you don't get rounding error. But either one would work. Okay, part C, find the magnitude of the velocity vector. What's another name for the magnitude of the velocity vector? The speed, right? Or the norm at t equals 2. So the magnitude, let's go ahead and use the notation. That's going to be the velocity vector at 2, and the magnitude is just single or double bars. It doesn't really matter which one. And that's just the good old-fashioned what? P theorem, right? The square root of x prime of 2 squared plus y prime of 2 squared. And let's see if we have enough of those pieces of information. X prime of 2 squared, I'm just going to go ahead and type that in as 2 sine of 4 squared. Again, that's the exact answer. Plus y prime of 2 is negative 6 squared. Now, if this were a calculator question, do I have to go any farther than that? Nope, that's an exact answer. That's not a very satisfying answer, but it certainly works. You could type it into your calculator and get a 3-decimal approximation if you want. If you did plug in x prime of 2 to be negative 1.513, and you went on to then simplify it, if your answer was off in the 3rd decimal, it would all of a sudden be wrong. So just be mindful that anytime you're going to use something that you've already rounded, you need to go back and either use the exact version of it or store that as a temporary variable, because you never want to use a rounded number. All right, I'll see how far we can get here before the end of class. Maybe time for one more. For t greater than or equal to 3, the tangent line has a slope of 2t minus 1. Find the acceleration vector at t equals 4. So working backwards, we want the acceleration vector at 4. That's the same as the derivative of the velocity vector at 4, which is going to be x double prime of 4, comma, y double prime of 4. Now, it's not going to be much of a problem to find x double prime of 4. Why? We have dx dt, right? So I can just let the calculator take the derivative of that for me at 4. But how am I going to find the second derivative of y if I don't have the equation for the first derivative? We'll have to talk about that tomorrow because we're running out of time. So there's a cliffhanger for you. And notice that is the very last thing we have to do for this whole section. So tomorrow we'll finish that. Maybe answer any questions from the worksheet. I know you're going to be working on them. And then we're going to roll right into Polar tomorrow as well. Yeah, we'll have a quiz as well. Thank you. Real quick quiz tomorrow. Yeah, just a short one. Over parametric and vector derivatives and accumulation. Probably one like the free response like we worked up here on number 1. All right, have a good